Hi Year 12, this is part 3 of the videos about the photoelectric effect. We've so far looked at the differences in the two models of light behaving as photons and light behaving as a wave, and we've looked at the structure of metals and what the electrons are doing inside the metals. In this video, we're going to look at the basically the experiment itself and what the results of that experiment are. So there's quite a lot to go through here. I'll try and make it as concise as possible. We're going to start by looking at the experimental setup itself. So if you're going to look at the photoelectric effect in a way that you can make measurements, you need first of all a cathode, and the cathode is the piece of metal that you are going to shine light onto. So this would be light from a source, and remember we said that we can change things about the light. We can change the color of the light, which we would talk about changing the frequency if we were thinking about it as a wave, and we can also change the intensity of the light, so making it brighter, in other words. So if we shine light on a metal, under certain circumstances we're going to see the electrons emitted. That's what the photoelectric effect is. So over here we want something that's going to collect the electrons, and something that absorbs electrons we call an anode. So a cathode is defined as something that emits electrons, and an anode is something that absorbs electrons. Now, all of this would be happening in a vacuum because the electrons aren't going to travel particularly far in air. And what we also need to do is we need to connect these two electrodes in a circuit. I'm going to put a couple of things in this circuit. First of all, we're going to put a variable voltage supply. So I'm going to draw that like that. And we're also going to put something to measure the current in the circuit, an ammeter. So you'll notice that I've connected the DC voltage here so that the anode is connected to the negative. So just to emphasize that, let's put some negative signs on there. Equally, we could put the cathode on there. So the anode is a negative potential compared to the cathode. What that means is that the electrons that are emitted from the cathode, as they start traveling across the gap towards the anode, they're actually being repelled. So they will be slowing down as they cross that gap. By changing the size of that potential difference, by changing the voltage, we can begin to not only slow down those electrons, but stop them and reverse their direction. So as we do this, if we imagine we're shining light onto the cathode, electrons are being emitted. If we turn the voltage to 0, we would expect the electrons to travel across the gap with a constant velocity. If we start making the anode negative, the electrons are going to be slowing down, and some of them may then begin to not reach the anode. And so as we change the voltage here, we're going to see a difference in the current in this circuit. Okay, because the electrons, once they've crossed the gap, they will flow around that circuit. So that's obviously a very simplified version of the experiment, but that gets across, I think, the main features of the design of the experiment. So what that means is that by changing the voltage, measuring the current for each voltage, and doing a little bit of calculation, we can work out the distribution of kinetic energies that these electrons have. And so if we did that experiment, what we would end up with is perhaps a graph that looked like this. We've got the number of electrons that have a different amount, different values of kinetic energy. And if you do this experiment, you see something that looks something a little bit like that. Okay. So what this graph is showing us is that the electrons that are emitted from the cathode when we shine light onto it have a range of different kinetic energies, varying from 0, so they've just escaped from the metal, but basically they're not moving, up to some maximum value of kinetic energy. We're going to define that value. We're going to call that EK, max. Okay, so that is the fastest electron that's coming out of the cathode. Now, another thing that we could do with this apparatus is change the frequency of the light, change the color of the light, or change the photon energy of the light if we're thinking about it in terms of photons. And this leads us to our sort of first kind of key result of the experiment. If you change the, we're going to call it frequency, okay, because we need to be able to put a number on it. And remember, when this experiment was first done, people didn't really know about photons, or they didn't think they were necessarily real. Our understanding of photons is really a result of doing this experiment. So they would have been thinking about this in terms of changing the frequency of the light. And for each frequency, we could measure this property. We could measure the kinetic energy of the fastest electron, the most energetic electron that's emitted from the cathode. Now, if we do this, we start at some quite low frequency. Obviously, this wouldn't be 0, but some quite low frequency light. What we see initially is that for low frequencies, we don't get any electrons emitted. There is no photo emission. As we increase the frequency, we get to what's referred to as the threshold frequency, where we start seeing electrons emitted. Once we start seeing electrons emitted, as we increase the frequency further, we see a linear relationship between the maximum kinetic energy and the frequency of light that we're shining on the surface. So there are two results here. The first key result of this experiment is the existence of that threshold frequency. Okay, and we're going to define that. We're going to call that F0. So that is the key frequency. If the light is below that frequency, no photoelectrons. If the light is above that frequency, we get photoelectrons. And the second observation that is important here is that if we then continue increasing the frequency of light, then the kinetic energy of the most energetic electron depends linearly. So it's a straight line, this graph, in other words. Okay, so EK max depends linearly on frequency of light. Okay, so what else could we do? We talked in the first video about how we could change the frequency or the color of light. Another experiment we could do would be to fix the color of light. So we're using a fixed frequency and change the intensity of light. Okay, so in other words, we're using a fixed color of light and we're changing the brightness. So obviously this fixed frequency of light we're using would be above the threshold frequency because we want to see some electrons being emitted, and we're going to change the intensity of the light. If we do this, we can look at the effect of the intensity on the flux of electrons. So how many electrons per second are leaving this cathode of a certain area, and because those electrons are going to flow around the circuit, we could describe that as the current. Okay, so I'm going to label this axis here as the current. Okay, so it's the flow of electrons around here. So if we change the intensity of light that we're shining onto the cathode, and for each different intensity we measure the current. Okay, so we're fixing some fixed value of the potential here. We're not changing that anymore. We get a relationship that looks something like that. Okay, so as we increase the intensity, the current increases. In other words, more electrons per second are being emitted from the cathode. So that's our third observation. So for a fixed frequency, the current depends on intensity. And that relationship as well is a linear relationship. It's directly proportional, in fact. So if we have zero intensity, that means no light is shining on there. Unsurprisingly, we don't get any electrons emitted. And then if you double the intensity, you double the current. The final observation, final result of the photoelectric effect is that when you turn the light on, we get an immediate current reading. And that's true regardless of the intensity of the light you're using, providing we're above the threshold frequency. It's also true regardless of what the frequency or the color of the light is. Okay, so the fourth observation we can summarize as the emission is immediate. There's no time delay between turning on the light and essentially observing the electrons being emitted from the cathode. So that's those are the key results from the experiment, and in the next video we will look at trying to interpret those results and think about what they tell us about the nature of light.